So I will just make a quick remind of the topic that was discussed last week. So basically, we have identified two types of superfluid systems. This is condensed matter physics. So it was a superfluidity helium-3 and 4, as well as superfluidity of electrons in superconductor. In both cases, this viscosity was going to zero. So essentially, the system has no dissipation. So this was a like transport without a friction. And both theories were described by a mean field Ginzburg-Landau theory. So in one case, it was nonlinear Schrödinger equation, where there was the size of Cooper pair was the size of coherence length of superconductor. And in another case, it was a Gross-Pitayevsky equation that takes place in Bose-Einstein condensates and in highly diluted gases, as well in superfluid helium. You can have it. So essentially, so today I will talk more about superfluid helium. That is a kind of very rich condensed matter system. So yeah, so there is a bunch of topics that are concerned with helium-3. And in the famous Volovik book, Universe in Helium Droplet, you can recognize that there's a scenario of formation of topological effects. There's a scenario of boundary between coherent microscopic wave function and non-superconducting state. There is a lot of things that deals with phase transitions in helium-3. So, and there are also some effects of some cosmological effects, like Big Bang theory, like inflation. Some people try to attempt by usage of this theory of a condensates. If you have some questions, please give me some of the questions by chat, right? All right. So so there is this is a very rich book, and I'm going to give you a little hint in this introduction. There's a bunch of phenomena that are concerned with black holes in condensed matter systems. So there's a scenario for transition from quantum hydrodynamics to classical hydrodynamics, and so on and so on. Okay, I will try to move to more simple slides. That's one of the slides by Volovik, by the way. All right, so this picture is kind of commonly known. I have described this picture 1 week ago, and I believe a few times before last week. So basically, we have a situation where we have superconductor, and when we try to, which has a condensate of electrons with spin up and spin down, and essentially in such system we have formation of quasi-bosons that have net spin set to 0, so there's spin up and down. And if such system is placed in external magnetic field, obviously the magnetic field starts to rotate the spins into one direction. So because of that, there is destruction of a ground state of superconductor. And the superconductor is trying to defend itself, so there is induced vector potential in the condensate. And because of that, we have the situation that when there is a screen current that goes around the superconductor, and the screen current is trying to compensate the effect of external magnetic field, and so we have such situation that the screen current is trying to defend the destruction of a ground state in superconductor. In case of superfluid systems, there will be rotation of. So in screen current, there are always two components of current. That is superconductor current or non-dissipative current and normal component of current. And we have this. Yeah, so that's quite interesting. So then I also mentioned these issues connected with Josephson junction. But in a superconductor, we have this quantization of magnetic flux, and in superfluid system, we have quantization of magnetic flux. And that was the case of occurrence of vortices in a superconductor. So if you place superconducting slab in external magnetic field, what happens is that first there is induction of the screen current. And there is occurrence. So this is this arrows, and simply there is occurrence of destruction of the superconducting order parameter in the core of superconductor. So we have a vortices formation, and then there is non-dissipative current flowing around the core of vortex. And then this vortices occurs because of you can get them from solutions of Ginsburg-Landau equation or Gross-Mitajewski equation. And yeah, there is characteristic superconducting flux quantum that is being used later in electronics. Yeah, so there was discovery of superfluidity in helium in 1938 by Kapitsa and others. There was characteristic Fontaine effect that was observed. And there was a conceptual similarity of superconductivity with superfluidity. So, and this conceptualization was quite correct. So what did happen was there was a big connection. In the 50s, there was Ginsburg-Landau theory developed, and in the 60s, there was BCS theory for theory of superconductors, and there was this distinction between superconducting and superfluid phenomena. So basically, we can call it superfluidity of electrons is responsible for superconductivity, and superfluidity of helium-4 or helium-3 at very low temperature is responsible for a superfluidity. And in all such type of systems, you can construct Josephson junctions. So, so we have this, and then we have characteristic creep of fluid across the walls of containers. Yeah, so that's how it is. All right, I move on. So there is a richness of theory of superfluid or superconducting states. If we talk about superfluid, we have BCS theory. We can construct a Polish propagator in complex counter. There is Eilenberger propagator, Usadel propagator, and then we have real distance equations that are basically equivalent to BCS theory. And then we have further simplification of that. But it's Ginsburg-Randall equations that are only valued close to critical temperature. And above all of that, we have a two-fluid model that assumes occurrence of two phases, normal and superfluid, in a superconductor. So this picture is basically the same uh, for both superconductors and superfluids. And yeah, so I will move on. Yeah, so I already described this C4 theory for superconductors. Original version is without this gradient. So we have uniform superconductor. And if you have alpha negative and beta positive, then and then if C square is density of electrons, then we have a two Taylor series, two Taylor terms, Taylor series, and they are in such a way that they induce non-zero superconducting order parameter. So you have actually this equation is extended with presence of gradients, and here is a canonical momentum for a superconductor that has to do with current flow. So if you have no gradient, then this is basically uniform superconductor. And there's also place for occurrence of magnetic field. All right. So by minimization of this functional, you can obtain a nonlinear Schrödinger equation that is Ginsburg-Randall equation and equation for current density. That's basically this fact is expressed here. Yeah, and again, this is this scenario from free energy functional and non-zero superconducting order parameter. So we have this formation of these vortices in superconductor. So those vortices are effects of magnetic field in the superconductor. And there could be pinning centers and so on and so on. So these vortices can have a complex topologies as given here. And there are various forces acting on these vortices, like Lorentz force. So it's like the core of vortex is a normal state. The vortex moves, there is a resistance, ohmic resistance. There is Lorentz force acting on the vortex-vortex interaction that is repulsive. The vortices has the same helicity. There is some force which is opposing vortex movement. It is proportional to vortex velocity, right? All right, so that's how it is. And then we have the comparison. There are some work on giving vortex some features of particle. So we have viscosity of vortex, and there is Lorentz force. This is a bit similar to mechanical force. There is critical current density, and there is maximum static friction, and so on and so on. There's this work made up from the University of Tokyo, but there is also work that is going before this work that already derives particle concepts from this Ginsburg-Randall theory. All right. And there's also analogy with charge density waves. I'm not going to discuss this in detail, but there is also pinning force, and so So we have maximum static friction for macroscopic objects. We have critical current density for vortices, and we have the peak electric field that is allowing charge effects in charge density to move, anomalies in charge density. And there is a mechanical force, Lorentz force, and electric force. And there is also about quantization. We have vortices in the superconductor and electrons in charge density modes. All right, so there are vortices in superfluid, and they're quantized. Unfortunately, I'm in a restaurant, so this thing starts to be a little bit noisy. So last week we talked about this Gross-Pitayevsky equation. This equation can be derived from point-like interaction between atoms. That's how it is given here. And then I described Volovik equations, and there was a correlation of two annihilation operators that has to do with superconducting order parameter. And then the final form of Volovik equations is given here. And this is pretty similar to Dirac equation. So there are some analogies with harmonic oscillator. Talking just about superconducting state, we have many-body state that can be written in such a way. So basically, vacuum superconductor is Fermi liquid. So we have this such many body particle state given as by its formula. And then we have mentioned that we have this vacuum in helium-free and vacuum in Dirac electrons. So basically, we have this analogy of mass to superconducting order parameter. So we have this Dirac vacuum and vacuum standard model. And then there is a spectrum of excitations that is typical for superfluid. So we have energy given in case of rotating Q, we have momentum of rotating container given here. And the spectrum of excitation is given us here. So basically, we deal with, so if we talk about high temperature superconductors, we talk about the system which has Hamiltonian written in such a way. So there is tau free is sigma free matrix. Tau 1 is sigma 1 matrix, and tau 2 is sigma 2 matrix. And this is a feature of D-wave superconductor. That's an isotropic superconductor. So we have this will be very important. There will be later a very important analogy of helium-3 and P or D wave superconductivity that will be presented. So we have this eigenenergy spectrum for Volovik equations. So we have two situations. There is with superconducting gap and without a superconducting gap, that's given here. And yes, and then now I'm going to give some analogies between superconducting state and superfluid state and general relativity. So first of all, we need to identify this the equivalence of. We need to identify the equivalence of speed of light in the superfluid systems. So in case of superconductors, there's maximum allowed speed. That's maximum allowed speed, and in superfluid systems, that's if you cross the speed, then you move into normal state, in this dissipative state. Similarly, in superconductor, if you cross certain value of vector potential, it simply becomes your state will move out of superconducting state. So there's a like maximum allowed speed. And this maximum allowed speed is a kind of like speed of light. So you have particles and tachyons that move above the speed of light, but it can never move slower. And the same is with superconductors. That there are some phenomena some phenomena the particles move with the speed of up to the speed of light. So yeah, perhaps I will describe this in a deeper way in some time. So so there will be, if you have a condensed matter systems, then what you have is you can deal with various dispersion relations. One type of dispersion relation is when you have zero superconducting order parameter. Another type of dispersion relation is when you have non-zero superconducting order parameter. So one will be typical for photons when you have zero superconducting order parameter, and one will be typical for other particles different than photons. All right. Yeah, so I will now characterize this under reflection that has very nice, it's a bit analogical situation with the situation of a black hole. So so you can have like particles that are like electrons coming to, so if there's movement of electron coming to superconductor, and this movement is in normal state, it's reflected as a whole. Hole is like antiparticle of electron, and such situation is taking place. This is like Hawking radiation, where you have more particle approaching the black hole is later kind of reflected as an antiparticle. I'll mention about this effect later. So anyway, in superconductors, in original superconductor with a singlet phase, when we have electron and anti-electron correlated together, and there is net spin set to 0, net angular momentum set to 0. This is singlet state. However, is it possible to connect two electrons? So there's induction of a triplet phase, and there's appearance of this triplet phase, and four electrons have the same spin. So there are three possible scenarios. So they have +1, -1, and its projection of spin is 0 in the first case. So you are given by such situation. Yeah, so essentially SY theory describes BCS state. It was modeled for Schleifer theory in 1957. And a kind of 14 years later, 1971, was discovery of transition helium-3 to become a fermion system to a boson system. It's done at very low temperature, 2.6 millikelvin, the distribution refrigerator. And this is this original experimental results are given here. So we have a phase diagram of helium-3, in which we have, so basically helium-3 is slightly lighter than helium-4, right? So essential difference is that we have 2 protons and 1 neutron in the nucleus. So in helium-3, nucleus spin is unbalanced. It's 1.5, and this brings yeah, so difference with helium-4. So this difference is especially pronounced at very low temperatures, like essentially much below 2 Kelvin. So yeah, so we have Fermi liquids in this. So we have pressure versus temperature diagram. There's Fermi liquid, and then there are 2 superfluid phases, A and B. If we increase the pressure, we have ordered phase with ordered spins, or at higher temperature we have disordered spins. The recurrence is logarithmic scale here, and linear scale here. So there is solid UCC here. So then simple liquids of helium-3 is isotropic short range, extremely pure. Some people used to say it's the most pure in nature. Yeah, and there's nuclear spin. The system, two superfluid atoms are neutral. Yes, then we have characteristics of helium-3. So, of superfluid phase. So we have such a situation where we have magnetic fields that affect the spin direction, obviously. We have temperatures, and so we have pressure. And so we have a situation where we have three phases, A, B, and normal. I'm going to discuss those three phases. So yeah, so let me move to phase A. So phase A and B deals with a triplet phase where spins up and down occurs equally. And we have in A phase that is reserved for higher temperatures, as we see, higher magnetic fields. We have anisotropic in superconducting order parameter. So since we have a triplet phase, it's like P wave. So in P wave, the value of superconducting order parameter for P wave superconductor is dependent on the direction. So we have at those 2 points, 2 nodes, we have this this superfluid density of superfluid order parameter. And here we have in this nodes, 2 nodes, we have maximum value. So that's how it is. And yeah, so you can say those 2 directions occur with the same, those 2 phases occur with the same ratio. Spin up and so plus and minus 1. And this superfluid phase allows to understand exotic superconductors. Probably the most exotic is UPT3, uranium plutonium-3. You need to have a lot of permissions to study such material, because you need to have a permission to study uranium, you need to permission to study plutonium. Compounds of that is very heavy and so on, and also radioactive. It's a very interesting superconductor. Yeah, so then we have D phase of superfluid helium. And this D phase is also very interesting. It's a superconductor phase, but have spins up, spins down, and net spin projection is set to 0 for some cases. And this phase has a unique feature. It's isotropic. It's almost like S-wave, but not exactly S-wave. You see, this is reserved for ground state of this helium-3 system. In the ground state, there is the ratio of all projections occur with the same rate. So there is no case of spins of atoms generating with magnetic field. It's very pure phase. So this interior of this phase transition diagram is connected with B phase, and exterior is connected with A phase. And above that, we have a normal phase and so on. So this is pseudo-isotropic state, like almost as a superconductor. And there is characteristic lambda transition in heat capacity is observed. There is also appearance of A1 phase. In A1 phase, we have promotion, one type of projection of a spinning triplet phase, with spin up, for example. And this is long-range ordered magnetic liquids. And now, in order to exploit this different systems with various types of order parameter, it's very interesting to observe, for example, AB interface. So in AB interface, we have helium 3A phase and helium B phase. Helium B phase is vortex free. And as you see in helium A, vortices are bending. So there is AB interface. So there's interface between helium A and helium B, right? Just to remind you, helium B is the most pure, has the same ratio spin up and spin down. And helium, so helium B has such three equal components. Helium A has on up or down. There is formation of so everything takes place in cylindrical container that is rotating, and so it's probably instructive to show you this case with in a real experimental device. So it's basically like here. So we have a situation where we can have two types of phases. So we have it all depends how you rotate liquid helium. So we can have various dynamics, various topologies of vortices. And clearly here we have a situation of AB phase. And then we can have, so initially we can have like equilibrium vortex state, and then we have rotating helium 3, then A and B phase, the formation of such vortices as described here, right? So right here. There's also a case of turbulent bursts where superfluid vortices are entangled. So please recognize that lattice, so things are kind of connected. Yeah, so that's, I'm going to give you just a draft of the situations that you might recognize in your real experimental systems. They're hardly experimentally accessible because you have to do 3 millikelvin, more or less. because one of the lowest temperature you can get with dilution refrigerators is not that easy. It's very expensive, by the way. But this AB interface represents rich dynamics. Yeah, so you have helium A. So helium A has this anisotropic superfluid order parameter. Two nodes where they show this gap in excitations. Yeah, and then you can look for eigenenergies of such a system. There is component connected with kinetic component, this is this one. And the component that is connected with superfluid order parameter, that is dependent on direction. And then there is this magic interpretation that you can recognize those elements as a product of some tensor of some space, so space metric times angular moment times momentum components, and there you can talk about Lorentz invariance and such type of metric for in here. So that's quite essential recognition of this kind of space curvature in such type of systems, how you can reinterpret occurrence of this space curvature due to occurrence of isotropic superconducting order parameter or isotropic superconductor order parameter, superfluid or superconducting order parameter. That's kind of greatly discussed on many in this Volovik book. Okay, so so there are some scenarios of approach of comparison helium-free system as a system modeling the formation of the universe, and there is characteristic breakdown of the symmetries that takes place in superfluid helium. So we have SO3, U1, symmetry breakdown to U1, and SO3. This is superfluid scenario, helium-free. Or we have SO10, SO3, SO2, SU1, and breakdown into SO3 and 1. And obviously, there are some characteristic energy scales like Planck scale, retinification theory scale, and electroweak scale in Big Bang theory. And there are some counterparts of this theory. So essentially, in helium B you have SO3 symmetry. Helium A you have U1 symmetry. Yeah, I will discuss these things in greater detail later. So, okay. So I'm going to, I'm almost done. So I'm going to just to bring some summaries. So there is, so I will continue this lecture in greater detail next week. Essentially, we have vortices occurrence as the modeling cases of occurrence of molecules as excitations of vacuum. That's in case of superfluids with helium. And this helium-free and has a richness of behavior, so it can also we can also model this Kalman vortex, Merton-Hall vortex, and so on and so on. So I discussed today this occurrence of superfluid B and A phase, a normal fluid. And there are some energies with P wave and D wave superconductors, right? And we have transitions between helium-free, that is normal phase, to helium-free A and B as two superfluid phases, as second order phase transition. Right, so, and we have a bunch of broken symmetries. So here there are different dispersion relations, and in this direction we have a like photon-like dispersion relation, and here we have a like particle with mass dispersion relation. Yes, there is a richness of behavior. Some people used to say that helium-free is a central concept. You don't need to study the whole physics, you need to study helium-free. And you can have a like Big Bang theory, helium-free. So everything is ordered at an initial stage, and later this order is destroyed. Okay, maybe this absolutely beautiful picture is UPT-free, uranium plutonium-free. 2 atoms for atomic bomb. It can be used in one experiment. And such system is radioactive, has an isotropic order parameter, and so on and so on. So you can observe this vortex formation by observing the behavior of helium-free, for example. All right, so I guess it's good time to stop here. Oh, and I welcome your questions. So having your questions, and I believe it's kind of desirable to talk about those things next week as well, and to pay greater attention to these analogies of black holes in condensed matter systems. So please give me some questions. So I wait your questions, please. Possibly on the chat or by unmuting, it's up to you. All right, so if there are no questions, I suggest we meet next week, and let's hope to finish this topic. But this topic is, it's good to have some nice lecture of Volovik, hoping in greater detail. This kind of, this book is quite challenging, I would say. So let us have some insight, and see you next week. Have a nice weekend.